Okay. Good afternoon, all of you. So let us start with the lecture. Less participants are there. 41 participants are only there for the lecture. Why the attendance is so less? Okay. Anyways, uh, just tell me whether the screen is visible to you.
Yes, ma'am.
Okay. Okay. So uh, today in the morning lecture, we have seen the different phases of compiler, how the compiler works, what is the input and output provided to each phase, and how the compiler detects the error, and how every phase of compiler is attached with the error handler and symbol table. So symbol table is a data structure which is holding all the tokens of the source program into it along with their attributes. So a token, whenever it is encountered or any variable, the it is getting stored in the symbol table, and the corresponding attributes like data type and the size of the variable, all those things are getting stored in the symbol table with their value, etc. So all those fields are used by the further phases of the compiler. So intermediate code or even code generator, code optimizer makes use of this information from the symbol table. Then we have seen the error handler. So error handler is again commonly joined with all the phases, which is giving the error correction subroutine or error detection, we can say. So every phase detects the error at the time of compilation process, and that are taken care or that are displayed by the error handler along with the line number. Okay, so this much part we have covered. With one example, we have seen how every phase performs or how the compilation takes place for the given example. So this much part we have covered, and now we are going to see the last bit of this chapter number 1, and that is compiler construction tools. So as the name rightly suggests, it constructs the different phases of the compilation. So we have already seen there are 6 phases of the compiler: lexical analyzer, then syntax analyzer, semantic analyzer, then intermediate code generator, code optimizer, and final code generator. So these are the 6 phases. And what is the job of compiler construction tool is, so they help us to develop a phase as a tool. So instead of writing the compiler as a whole, we can divide the compiler into number of phases, and each phase is acting as a tool. And we are having the separate tool for maybe lexical analyzer, maybe for parser. So all these things are nothing but a kind of tool, and we are making use of it for simplified compilation process. So that is the benefit of compiler construction tools. So let us read the theory part. The compiler writer, like any programmer, can profitably use tools such as debuggers, version managers, profilers, and so on. So like a normal programmer, whenever we want to develop any software, whenever we want to develop any project, then we are going to concentrate on the tools like debugger, then version manager, and profilers. So these are the tools that are used by every programmer. Similarly, in order to design a compiler, we are going to add some more tools. So in addition to these software development tools, other more specialized tools have been developed for helping implement various phases of compiler. So they act as a phase of a compiler. So a tool is getting developed. So I'm developing a tool to which, if the source program is provided, then it works similar to the lexical analyzer. It works similar to the lexical analyzer, and as an output, it should provide the tokens. It should generate the tokens of the source code. So whatever the source code is provided, the tool is developed in such a way that the outcome of the tool is number of tokens. Ultimately, the tool is mimicking, or it is performing the job of the lexical analyzer. This tool is acting as a lexical analyzer because the source program is given and number of tokens we are getting as an output. So we are going to use the more specialized tools for helping implement various phases of a compiler. So here is a one tool which is acting as first phase of the compiler, lexical analysis. Similarly, the another tool I can use, which is called as syntax analyzer, or it is also called as parser. So whenever the tokens are provided as an input, like your second phase of the compiler, whenever token is given as an input to the syntax analyzer or parser, its job is to generate the parse tree. So it is going to generate the parse tree out of these tokens. So these are the small units of the project. In short, these tools are nothing but the small parts of the project. First unit or first tool is acting as a lexical analyzer, second is acting as a parser. So ultimately, whenever I am generating these small parts, they will help me to implement the compiler, right? They will help me to implement the compiler. So that is the basic idea behind the compiler construction tools. So shortly after the first compilers were written, systems to help with the compiler writing process appeared. So whenever the compiler is written, then after the systems to help with the compiler writing process appeared. So here we are having the system to write the compiler or the process of the compiler. These systems have often been referred to as compilers or compiler generators or translator writing systems. So as they are the part of the compiler, they often called as compilers. So these are the compiler construction tools which acts as the smaller portion of the compiler itself. So these are the tools which acts as the smaller portion of the compiler, and that's why the name is given as compiler, or they generate the compiler as a whole. So when I group these tools together, they will form the structure of a compiler, and that's why they are called as compiler generators, or they are also called as translator writing systems. Ultimately, the job of the compiler is to translate the one high level language into low level language, and that is called as translator writing system. So compiler is nothing but the translator writing system. Then some general tools have been created for the automatic design of specific compiler components. So we have specific design for specific tools or components of the compiler. These tools use specialized language for specifying and implementing the component, and many use algorithms that are quite sophisticated. So in order to design this tool, the tool which should act as a lexical analyzer. So this is a tool, and to make this tool work as the lexical analyzer, we have to write some code in it. We should write some code, and that are nothing but the algorithms that are quite sophisticated. So whenever we are writing any kind of tool, then we have to use algorithms which are sophisticated in nature. The most successful tools are those that hide the details of the generation algorithm and produce the components that can be easily integrated into the remainder of the compiler. So how we are going to detect that the tools which are generated are successful tools or good tools to use, right? Because we are generating some tools. They will help me to implement the compiler, but how to check whether these tools are really good to use? So for that, they have given the two conditions. First is they should hide the programming details. Obviously, if I know these algorithms, so the only programmer should know the algorithm, what exactly is written in the algorithm. Otherwise, the users are only using this tool. So what is the job of the user? Just to provide the source program and to get the token as output. So they don't have to worry about what is written in the code because they are the users of the compiler. So their job is to convert the source high-level language into tokens as that of lexical analyzer. But what exactly is written here should be hidden from the user. It should be known only to the programmer. That is the first quality of good compiler construction tool. So the most successful tools are those that hide the details of the generation algorithm. It is the one criteria that it should hide the details of the algorithm. And second is it should produce the components that can be easily integrated into the remainder of a compiler. So if I'm building this lexical analyzer, it should easily get fit to our remaining phases of the compiler. So these are the 5 remaining phases, suppose. Right? So I am building one lexical analyzer. How I'm going to check this is a good lexical analyzer? That the code should be hidden. And second is it should easily get integrated with the remaining phases of the compiler. So these tools should easily get mixed with the other phases. And that is the second requirement to be most successful tools. So let us see now the examples of such tools. So these are the 5 examples, 5 tools available. They are also called as compilers or compiler generator or translator engine. That is nothing but the translator writing systems. Okay, so these are the compiler construction tools. So first is the scanner generator. The scanner generator is also called as lexical analyzer because it is scanning the source input and converting it into the tokens, and that's why the name is given as scanner. So we have a readily available tool which is called as scanner generator. Second is the parser generator. So what is the parser? Parser means it should act as a syntax analysis phase. So the parser generator is a compiler construction tool, and that should act as a what we can say, that should act as a syntax generator. The third is syntax directed translation engine. So use of this engine is to evaluate your tree. So once the parse tree is generated, the evaluation of that tree is carried out by using syntax directed translation engines. Maybe you are going to calculate the tree from top down or in bottom up way. So depending upon the approach, you are going to calculate the value for that tree, and that is done with the help of syntax directed translation engine. Then we have fourth tool, which is the automatic code generator. So it is the last phase of the compiler where the target code is getting generated automatically. Target code is getting generated automatically. And the fifth is data flow engines. So data flow engine has to do with the code optimization. Why the name is given as data flow? Because it will check the flow of the data through different variables, and whenever required and whenever possible, it performs the optimization. So depending upon the data, how it is passed from one variable to other, then how the calculation is carried out, these all things are checked in the data flow engine, and they are responsible for optimization of the code. In short, we have these 5 compiler construction tools. Scanner generator, it acts as a lexical analyzer. Parser generator acts as a syntax analyzer. Syntax directed translation engine, it acts as a semantic analyzer, or it performs the evaluation of the tree. Then automatic code generator, it acts as a final code generator, and data flow engine acts as a optimizer. So these are the 5 tools. So let us see each tool in detail. So first is parser generator, or we can see the scanner generator, because the scanner generator is acting as the lexical analyzer. That is the first phase of the compilation process. So what the scanner generator performs? So these tools automatically generate lexical analyzers. So what they are doing, scanner generator, they automatically generate the lexical analyzer. And then what is the job of the lexical analyzer? To generate tokens. Normally form a specification based on the regular expression. So here the regular expressions are used to generate the tokens, to check the rules, whether these fit into a kind of token or not. And for that purpose, the regular expressions are used. Okay, so scanner generator is nothing but it generates the lexical analyzer automatically, and it specifies certain regular expression. The basic organization of the resulting lexical analyzer is in effect a finite automata. So we will see in the second chapter how we are going to make use of finite automata to design a lexical analyzer. So the basic organization of the resulting lexical analyzer is in the effect a finite automata. So ultimately, the job of finite automata is generating the scanner. Then what is parser generator? So they produce the syntax analyzer. So here scanner produces the lexical analyzer, and parser generator produces the syntax analyzer, normally from input that is based on the context-free grammar. So always we know that parser makes use of grammar given, and then the tree is generated, and then it is either evaluated in bottom up or in top down way. So here, based on the context-free grammar, you are going to produce the syntax analyze. In early compilers, the syntax analysis consumed not only a large fraction of the running time, but a large fraction of the intellectual effort of writing a compiler. So while learning the third chapter, syntax analyzer, we will come to know what is the meaning of this. That is, syntax analyzer, I already told you, this chapter consumes almost 1 month to cover. So it is very vast. Similarly, writing the syntax analyzer is also a quite critical job. Like it has a large, it consumes a large fraction of the time. So in terms of running time, is also complicated, but it also requires the intellectual efforts of writing a compiler. So whenever we are writing a parser, the more intellectual efforts are required. This phase is considered one of the easiest to implement. Though while writing, there is complexity, but while implementing, this phase becomes very simple because the development is a complicated one, and that's why we are going to get the output or going to get the implementation in very easiest. So these are the two tools. Next is syntax directed translation engine. So in syntax directed translation engine, they produces collection of routines that walk the parse tree. So we know that once the parse tree is designed, so earlier example, we will take the same example, A equal to B plus C into D. 10.0 suppose. Okay. Okay. So in this example, syntax directed translation engine means what? This parse tree we are going to evaluate. That means ultimately we are going to evaluate the value for A or the value for the root, in short. So it is the mathematical expression, and that's why we are having the value for A. But if it is a statement, then we are going to determine the value for the root. So that is the basic idea of the parse tree. Now, in this syntax directed translation engine, what we are going to do is they produce collection of routines that walk the parse tree. So we can have the number of ways to traverse this tree. So it is nothing but the collection of routines. These are the various paths available to traverse the parse tree, and which generate the intermediate code. So whenever I am traversing through variety of ways, I may generate the different intermediate codes. For example, if I am having a bigger tree, if I am having a bigger tree like this, B into C minus and let's say T. Okay. So suppose this is a bigger tree. So I can have n number of ways to traverse this tree. First, I will perform S into T, that I will store in some T1. Or first I will perform D minus E, then I will store it in temporary variable T1, or I will perform B into C, I will store it in T1. Similarly, I may traverse in variety of ways and I will evaluate the tree finally. So while traversing it in different way, you will generate different intermediate codes. Okay, you will generate different intermediate codes. The basic idea is that one or more translation are associated with each node of the parse tree. So for every node, we have one or more translations attached. So here, for every node, we are having one or more transitions or translations. And each translation is defined in terms of translation at its neighbor nodes in the tree. So already we know that whenever we are doing this C into 10, we are calling it as a T1. Then T1 with B, we are calling it as a T2, and so on. So the translations are there, and each translation is defined in terms of translation at its neighbor nodes. So T2 is further dependent upon T1 because T2 is equal to B plus T1. Ultimately, T1 is dependent upon their neighboring nodes C and 10.0 accordingly. So syntax directed translation engine, it will solve the expression, or it will evaluate the root node, and the evaluation is dependent upon the neighboring nodes, and we can have number of paths which will give me the number of sub expressions. So this is my syntax directed translation engine. So once you have this tree, you are able to generate directly the intermediate code, or it is also called as tree address code. The next is automatic code generator. So automatic code generator, the name itself gives you idea that it is the final phase. So it generates the target code. Such a tool takes a collection of rules that define the translation of each operation of the intermediate language into machine language for the target machine. So how it takes the collection of rules? Suppose I am having a function like T1 is equal to B plus C. Okay, suppose I am having this intermediate expression. Whether it is an intermediate code, tree address code, yes, because I am dealing with the address of T1, B, and C. Maximum 3 addresses I am concentrating on. So now what automatic code generator is doing? What is the job of that? It considers the intermediate code or tree address code as the input, and it is converted into the machine language, or we can say assembly language also. Okay, so this acts as an input. Now, when this input is given, then the tool takes collection of rules that define the translation of each operation. So for this operation, it will consider the variations possible. So what are the different collection of rules available? Here, you will save this B in some temporary variable T2, C in T3, or you may save this B in some memory address, or you may save it in some register. So there are multiple options to handle these B and C variables. So as the number of options are there, you have the collection of rules. There are variety of ways to generate the final code, and you have to go with the efficient one. So one way is I can use the register assignment for those variables B and C. Similarly, I can go with the memory and assignment. That is, I am going to store it in some fixed memory location. Or even I can use some temporary memory locations for moving this B and C. So all these are the possibilities to generate the final code, right? So the job of this tool is it takes a collection of rules that define the translation of each operation on the intermediate language into machine language for the target machine. So then also, depending upon the target machine, if the target machine is your binary machine which accepts 0 and 1, then again there is variety that instead of assembly language I will be concentrating only on the binary language. So that is the possibility. Or so such number of collections are taken together, and best of which will be your final code, and that is done with the help of automatic code generator. And now the fifth one, that is called as data flow engines. So data flow engine act as the optimizer. Just now we have seen, so it acts as an optimizer, and much of the information needed to perform good code optimization involves data flow analysis. So how the data is moving. For example, uh, if I am having this B, C, D, E, S, T, and one more variable U in the program or in the statement, so source code. So source code has these many variables B, C, D, E, S, T, and U. Out of that, while generating the parse tree, I have used all the variables except this U. While designing the parse tree, what I have done? I have used all those variables, but U I have not used. That means though U has been defined, as there is no further use in my program, I can easily delete that. So deleting this variable U will not change the meaning of the program. That is one thing, right? Because U is not used anywhere in this syntax tree. So I can remove this U from the memory. So optimization is possible after the data flow analysis. That is how the data is moving from start to end. Now, after observing this data flow or after observing this parse tree, I came to know that this variable U is never used. So I can remove that. And that is achieved due to this data flow analysis. So much of the information needed to perform the good code optimization involves data flow analysis. The gathering of information, how values are transmitted from one part of the program to other part of the program. So how we are transferring the values. So here B and C values are multiplied and sent to the root node or we can say parent node. D and E is subtracted from the D, and then we are setting or sending that information to the parent node. So in that way, how the data is flowing from bottom to top or from top to bottom, it is observed to get the good optimization effects. Getting it, all of you? Yes. Yes, students. So these are the 5 compiler construction tools which are useful for generating the compiler, and that's why the name is given as compiler, compilers, or compiler generator. Okay, is there any difficulty in these 5 tools? Simply you have to remember the name and their working. The working resembling to which phase of the compiler. So only that much is required. Getting it, all of you? Yes? Tell me either yes or no. Yes, students. Getting it? Yes, third year students. Am I audible? Okay. Okay. So I'm getting the response in the chat box that yes. So I believe there is no doubt because it is a theory part only. You have to remember the name of the compiler construction tools, the use of those tools in generation of the actual phases of the compiler, and which tool resemble which phase of the compiler that you have to remember only. So that is about the compiler construction tools. So this ends with your chapter number 1. This ends with your chapter number 1. So let us start with the chapter number 2. Now just go through the contents of the chapter number 1. So I will show you the syllabus of the chapter number 1. And if you have any doubt in any of the point, then you can ask me. So this is the syllabus, introduction of the compiler. What is the meaning of the compiler? The different phases of the compiler and compiler construction tools. Is there any difficulty? Okay. So I believe there are no issues. So let us start with the second unit. So let me quickly share the PPTs. Okay. Okay. So that is about unit number 2. The name of the unit is lexical analysis. So we have seen every phase of the compiler, but now each phase of the compiler we are going to observe in detail its working, then how to design that phase, then what are the different measures taken while designing, what are the characteristics or use of that phase. So that all these things we are going to learn here. So this is the syllabus of the unit number 2, role of a lexical analyzer, input buffering, then specification and recognition of tokens, finite automata implications, designing a lexical analyzer generator. So these are the 5 points under this unit number 2. For this unit number 2 also, you have to use the same book, that is the book by Aho Ullman Sethi. So Alfred Aho is the author. So let us start with the unit number 2. So what is lexical analysis? So we have seen lexical analyzer is also called as scanner, right? It is also called as scanner because it is scanning the input source program. So it is scanning the input source program, and that program is getting divided into number of tokens. So the job of lexical analyzer is scan the input, and that's why the name is given as scanner, or lexical analyzer phase reads the source program and divide it into tokens. So now we are going to see what is the difference between token, lexeme, and pattern, because many times the all of you are getting confused between what is meant by lexeme, what is meant by pattern, what is meant by token, and all those things. So we will see with examples what is the meaning of these 3 terminologies. Okay, so this lexical analyzer is also called as subroutine or coroutine of the parser, right? Because the lexical analyzer is the first phase. After that, you are having the parser. So I will say here it is a scanner and this is a parser. So the scanner is also called as subroutine or coroutine of parser. Why? Because parser will ask the scanner to generate the tokens. Parser will ask the scanner. So parser is going to send the request of get next token. The job of parser is to generate the request for getting the next token, and this request is sent from parser to scanner. As soon as the scanner gets the request for the token, it generates the token by using the source code. So then the scanner will read the source code, and from the source code, it will generate the token and send it to the parser. So as the working of parser and scanner are interdependent, parser first generates the request, send it to the scanner, then scanner process that request and send the token to the parser. So these 2 things are interdependent, that is, they are dependent on each other, and that's why the name is given as subroutine or coroutine of parser. So scanner is also called as subroutine or coroutine, that is some portion of the parser itself. Scanner and parser together forms the front end of the compiler. What is the meaning of front end? Front end is nothing but the first 3 phases of the compiler. They act as a front end because they are dependent upon the source language. So they are language dependent, and that's why they are called as front end. And the remaining 3 phases, that is intermediate code generator, code optimizer, and final code generator, they are dependent upon the target machine, or the they are machine dependent, and that's why they are called as backends. So scanner plus parser forms the front end of the compiler. So that is the basic information of the lexical analysis. So it reads the source program, divided into tokens. It is also called as subroutine or coroutine of the parser because with the get next token request, it generates the token and send it to the parser, and they together form the front end. So let us see what are the roles of lexical analyzer. So very basic role we have already studied, that is to generate the tokens, right? So the main task of lexical analyzer is to read the input characters and group them into tokens. So first and very important job of the lexical analyzer is to read the source program and generate the token. Along with this token generation, now the lexical analyzer performs following tasks. So what it does first is, as it scans the input, right? Because the role of the lexical analyzer is to scan the input. It reads the input word by word or character by character rather. So as soon as it reads that input, it separates out the white spaces. White space means what? Maybe a new line. That means whenever I'm writing a program, I'm writing like this. I'm declaring the variable integer a comma b comma c. Then I'm giving semicolon, writing enter, and here I'm writing a equal to b plus c and so on, giving the semicolon. So the job of the lexical analyzer is to cut those white spaces present. So it can be a new line character, it can be a tab, it can be a space. So a space between two words, or even a new line character, or even a tab can be removed by the lexical analyzer. That means whatever maybe the code is given, int a comma b, suppose this is a code, then float c comma d, right? Program is written like this in different lines to make that program more readable. So the job of the lexical analyzer is, it is going to divide this into tokens, but before that it removes all the spaces in between. So there is space between int and a comma b. So it will directly write down in the table as int, there is no space present, a, then comma, then b, then semicolon. And immediately it will start with f, float. Float, then c, comma, d, and again semicolon. Okay, so what it is doing? It is removing the white spaces. Then white space can be a new line, it can be a tab, or it can be a simple space in between the two words. So all those spaces are removed in the lexical analyzer phase only. So converting your program into a tabular form with no space in between is the job of lexical analyzer. Okay, so it skips comment. Yeah, it is also very important that as soon as it finds the comment, it can be multi-line comment or it can be a single line comment. So whenever it encounters the comment, then it skips those comments because they should not be the part of your symbol table, because that is not the source language or the source code. They are just the comments provided in the program. So they should not be the part of the source code. And that's why the skipping of those comments is also done in the lexical analyzer phase. Okay, so first main task is to generate the tokens. Secondary task is to skip the comments and to remove the white spaces. Then very important part of the lexical analyzer is correlate error message with source program. So correlation of the error message. What is the meaning of it? Suppose semicolon is missing. Then I should know on which line that semicolon is missing. And that is achieved by correlating that error message with the source program. That is, the line number of the error is printed, and that is achieved by the lexical analyzer. So it counts the number of lines. It counts whenever the new line character is encountered, it will increase the count by 1. Number of lines count, it will increase by 1 with a new line character. So initially the count is 0 here before start of the program. As soon as it finds the new line character, it goes into the new line, then the count will increase to 1. So it makes us easy to correlate the errors, right? As soon as I know the number of line, that is the line number, then I can easily detect and correlate the error message for that line. And very important fourth function of lexical analyzer is pre-processing of macros. So what is the macro? So many times what we are doing is we are using the macros like hash define, pi 3.14, right? It performs hash define pi 3.14. It means whenever I am performing the lexical analysis phase, or whenever I am doing the lexical analysis of the source program, wherever pi variable is there, that gets replaced by 3.14. So this replacement takes place in the first phase, that is lexical analyzer phase. Okay, all of you are getting this, the different roles of the lexical analyzer. So token generation is the main task. Along with that, the comment separation, white space separation, then correlation of the error with the line number, and macro execution or pre-processing of macro. So all these are the roles of lexical analyzer. So just now we have seen this diagram, role of lexical analyzer. When source program is provided, then it generates the token by scanning that program. So it will scan that source program and it will generate the token on the request from parser. That is, get next token is the request done from the parser side, and as soon as it gets that request, it will generate the token and send it to the parser for drawing up the tree. At the same time, it makes the entry in the symbol table as well. So lexical analyzer or scanner makes the entry in the symbol table about the generated token. Okay, so these are the main roles of the lexical analyzer. And one more thing is reporting of the errors. So we can say that here are also errors available, or error handler is available, which is connected to every field or every phase of compiler. Okay, all of you are understanding this role of lexical analyzer? Okay. So the errors which are encountered in lexical analysis are, so let us learn what are the lexical errors. So lexical errors, for example, the statement fi in bracket a equal to f. So here fi is misspelled keyword because I need to write if, but by mistake it is written F followed by I. It is a replacement of I and F. But the in lexical analyzer, the token is not getting generated. Why? Because Fi, it is not finding any keyword which is uh, having or it is a keyword if if, but for Fi it is not finding any keyword. So the error is not detected. This error is not detected in the lexical analysis as Fi is taken as the identifier. We have mistaken in this, we have misspelled the if, but what the lexical analyzer is doing, lexical analyzer is treating Fi as identifier and not the keyword, because it do not uh, check for the changing the position of the or making the spelling correct. So these type of errors are not handled with the lexical analyzer. It cannot detect it. This error is then detected in other phases of compilation. So whenever I am passing this information or passing this statement in other phases, then that error gets detected in the other phases. So in case the lexical analyzer is not able to continue with the process of compilation, it resorts to or it restores to panic mode error recovery. So what is the panic mode error recovery is? So suppose the job of the job of the lexical analyzer is to generate the tokens. Here, the token is not getting generated because Fi is not earlier declared as a identifier, integer or float or whatever may be the data type. So we are not declaring Fi, but it is used in our program. So such token is not getting generated in the lexical analysis. So for that, what is the solution given? Solution given is we can use the panic mode recovery, panic mode error recovery. The meaning is we can have multiple operations on this identifier. That is, we can alter the position of the words. We can delete all those variables till we receive a particular token. So deleting successive characters until the token is formed. So here with F, no token is formed. With I, no token is formed. So F and I am going to delete, and opening bracket is giving me the token that it is a special symbol kind of thing. So as soon as I get the token generation, I will stop deleting the characters. So all those characters are deleted. It is done in the panic mode error recovery method. So what are the different panic mode error recovery methods? Deleting the successive characters. So we can delete the successive characters. Just now I told you, as Fi is not producing any token, we can delete it from the remaining input until a token is detected. Second is delete the extra characters. So instead of uh, this keyword, if I have written IFI, if I have written IFI, so in that case, it will detect for the extra character, because if is the keyword, it has identified, but there is no identification for the further variable I. Such variables can be eliminated. So such extra characters can be deleted. So first way of panic mode error recovery is delete all the characteristics, all the consecutive or successive characters until we form a meaningful token. That is one way. Second way is delete the extra character. Then the third is insert a missing character into the remaining input. So suppose I have written a for loop and by mistake I have written fr for I equal to 0 less than 5 and I plus plus suppose. If it is the case available, so we can have insertion of the missing character. So here O is missing and we can insert that. Similarly, we can replace a character by another character. That is, if spelling mistakes are there, then we can replace the available character by another character or transpose two adjacent characters. So just now we know that with Fi, we can transpose the position of I and F, and I can get the correct keyword generation. So this is how in lexical analysis, if the tokens are not getting generated, then we can make use of those recovery methods. So remember those 5 recovery methods. Panic mode recovery is successive deletion of all characters till the token is generated. Second, extra characters can be deleted. Missing characters can be inserted, replacing the character by another character. And the last one is transpose. Transpose the position of the characters. So these are the different error recovery methods or techniques in the lexical analysis. Okay. All of you are understanding this? Is there any difficulty? Okay. So I believe no questions. So you can put your attendance in the chat box only once, and we will stop here for today. Write the attendance only once. The time is up already. So we will stop here. Till the other students are posting their attendance, if any one of you having any doubt regarding the first or second chapter till this point, you can ask. Xerox. If you have written your attendance, then you may leave. Roll number A19 is there?
Yes, ma'am.
Okay. Roll number A47 is there?
Yes, ma'am.
Okay. Roll number B61 is there?
Yes, ma'am. 61 present.
Okay. Roll number B32 is there? Anisha.
Yes, ma'am.
Okay. Okay. So if you have posted your attendance, you can leave. Thank you.